Today we looked into a little bit of PCA also. We looked into the eigenvector decomposition, eigenvalue decomposition. The principal component analysis uses eigenvector eigenvalue decomposition to find out the principal components, and then it projects and rotates. Okay, so when you look into eigenvectors and eigenvalues, it is characteristic vectors and characteristic values. Right? When a matrix has got some characteristic, if you decompose that matrix into eigenvectors, eigenvalues, the eigenvectors are going to be characteristic of, essence of whatever characteristic the matrix is having, and the magnitude of the essence extracted by each eigenvector is quantified by the eigenvalue. Okay, so this is a covariance correlation matrix, right? If you decompose this matrix into an eigenvalue decomposition, right, eigenvectors and eigenvalues, then the eigenvectors will have the correlation in them. You know? See, I have taken this matrix and decomposed that into two vectors. This vector, now suppose that if this is a covariance matrix or correlation matrix, this will have some, correlation extracted. This will also have correlation extracted. How much, which one has got more correlation can be found out by eigenvalue. Yeah, I need to change this to value. This is not vector. So this value, right, will actually quantify how much each of the vector is actually extracting the essence from the matrix. What is the essence? Whatever that, correlation or covariance or, co-occurrence. There are many different matrices we'll produce, and then we'll apply eigenvalue, eigenvector decomposition on it.
Sir, is it this x1 is 1 1, right?
Yeah.
So is the element of each element of the vector denotes correlation or the covariance between x1 x2, or is that something like that?
X1 x2 only. There are two variables here, right? So it's
Yeah.
going to be x1 x2. If there are 3 by 3 matrix, right, it's going to be x1 x2 x3. But you cannot say that, this first value belongs to x1, second value belongs to x2, like that. No. As a whole, it extracts the essence. That's it. It is like I said, sugarcane juice, right? The same thing. You
Okay.
cannot figure out from which cane how much, right? Whatever, how much juice came out. You cannot figure out once you put it into crusher, right? Eigenvalue decomposition is like crusher. You put these canes into crusher and it gives you the essence like that.
Okay.
But you'll know which glass has got how much, right? This is first class, this is second class. Now, first class has got more, second class has got less. This quantification is going to show you how much essence is been extracted into each eigenvector.
Okay.
This is the key for PCA. If you understand this, right, PCA is over. Okay. So let me. Is that it, or any other questions?
Yeah, that's it. I just wanted to know whether each element of the vector represents specifically
No.
the variance. Yeah.
No. But if you have, n number of features, right, you will have n number of eigenvectors, provided all those features are independent. Right, x1, x2, and so on, xn.
Okay.
Right, all features are independent. Then you will get, n number of eigenvectors. If they are dependent, right, those dependent vectors will go. Right, you will get, less number of. Go in the sense the eigenvalue is going to become 0. You may get some vector there, but eigenvalue is going to become 0. That means it's not at all important. We'll see that. Today I'll actually show you.
Okay, sir. Okay.
Explained variance ratio, we call it as in principal component analysis. We explain the eigenvalue. We'll see that.
Okay.
I think any other questions from anybody else? The eigenvalue, eigenvector decomposition or singular value decomposition is used in many places. One, principal component analysis. Second, word vectorization. Third, recommender systems. Fourth, I forgot. I know four of them. Latent semantic analysis. You know that that's algorithm name, but I forgot the concept. Text summarization. Okay. Linear algebraic way of text summarization also will use the same concept. Okay. If you understand PCA, right, the other things are going to be easy. Okay. So that's why I'm taking too much time here. So if you have a big data set, you know, in terms of columns, it takes lots of processing and all. You need to reduce it to less size. But the reducing data into lesser dimensionality is not the first task we will do. We take this original data, try to build a model and see how it's working. Provided y value is there, right? If you are trying to build a supervised learning model, right? And see how the accuracy is, and then we reduce the dimensionality and try to build a model again and see if we are getting the same accuracy or not. Right? After reducing the data, reducing dimensionality also, do you have the essence or not? How will you be able to check if the model is giving similar performance? Then we'll be able to check. Make sure, right? Not check. We'll be able to make sure that the dimensionality reduction worked well. Okay. So in a way, these unsupervised learning algorithms used as support for the supervised learning algorithms. Right? I'll come to that. Okay. So this is basically dimensionality reduction. You take a big, too many columns data set and reduce it to less number of whatever. So first we need to find out these principal components, this green line and the orange line, right? How will you find those principal components? Eigenvalue decomposition, eigenvector decomposition is the principal values. The green one is going to be the eigenvector with the highest eigenvalue, right? The orange one is going to be the next eigenvector with the next highest value. If you have third dimension also, it's going to be perpendicular to these two, and that's going to be the third one, right? Like that. So why am I saying this is the first one? Because most covariance, right? Most of the correlation is here. See, if you want to understand this as a layman, right? If I shrink, right? If I shrink all this data, let me try to now put this video also on. Right? Look at the diagram right here. Right? If I'm crushing all of them like that, right? The data is like this, right? Will the loss be more? Or if I crush all those, all these dots onto this line, will the loss be more? Crushing them onto green line will lose data essence more, or crushing the data onto the orange line will lose more data essence. It's a question.
Crushing on orange will lose the more essence.
Yeah. Did you, the other people, have you got that analogy? Have you got that analogy? Yes, no?
You're referring to the current points, right?
Your voice is low, sir.
You are referring to the current point, crushing of the current points onto the green line.
Green line or orange line?
Yeah.
When we crush it onto the green line, right, the loss is going to be low, right? The essence of the data, right? Original data is somewhere here. You are crushing it onto this data point means the data point will change, right? Yesterday I showed you 4.5 and 3.5 actually changed to maybe 4 and 3 or something like that, right? So the values will change a little bit. So we say this is the first principal component because the loss is going to be less. The most correlation, right? Most covariance, which is in which direction you will get the eigenvalue more. So first we need to find these, and then we need to crush them and then rotate them. Okay, like that. Right? First we need to center the data, right? And then find out the first principal component. Then push them, project them onto the this thing, right? And then again project those onto the second principal component. If you have n number of features, n number of principal components you need to find. The principal component is the direction in which the essence is being extracted. Then rotating is nothing but you are actually making the principal components as the axes to make to nullify one coordinate. If you don't do that, right, for each data point there will be x1 x2, again there will be an x1 x2 on the red orange one also, right? We need to have, for this x1 you need to have only a one x1, for this x2 there should be only one x2. If you make the other one 0, right, the first one will remain, right? X1 will remain here, x2 will remain here. So that way you are kind of changing the values and trying to extract the data. Okay, so as a layman, right, that's what is happening. It is trying to crush the data and then rotate it. Okay, so ultimately the total data becomes like this. These dots are the ultimate converted data. Okay, these lines are the eigenvectors. Okay, the orange line and the green line are the eigenvectors. These dots are the ultimately converted data. What is converted data? You took 100,000 and you converted them to 100. Right? You can actually convert them to 100,000 also. Okay, I am showing you that ultimate result is going to be like this. We'll see how it actually reduces to 100. But the process I showed you is like you take 100,000 and it becomes 100,000. Okay. Give me one second. So now, at original PCA we are going to talk about. The main goal of principal component analysis is to extract variance between features. Okay, this point is very important. The main goal of the principal component analysis is to extract variance between features. Give me one second. Give me one second. So PCA is actually trying to extract the variance between features, right?
So one question.
Yeah, please.
Sure. Yeah, can you go up a little? So for our ease of understanding, so here you have taken example between x1 and x2.
Yeah.
X1 and x2, two columns, two vectors you have taken. So in real time, how it will be calculated when there are let us say 1 lakh vectors or 1,000 vectors?
I'll show you. I am going to that.
Okay. Yeah. And also one more question is maybe you can. So this will be applicable to both linear data and non-linear data also, right?
No, only linear. Yeah, that's a good question. Non-linear we'll see. When it comes to non-linear, right, we'll apply kernel trick and then on top of it we'll apply PCA. We'll talk about it. That's a good question.
Okay.
Yeah. So both are very good questions. Anyway, I'm going to go in that direction. So this point is very important. The main goal of Principle PCA is to extract variance between features. So the matrix, right? The first point for eigenvector eigenvalue decomposition is that the matrix should be square matrix. On a rectangular matrix, eigenvalue decomposition we cannot apply. That's first thing. And the PCA is actually trying to extract the variance. So we need to create a covariance matrix of our data. See this? This is my data, right? What is the covariance formula? Do you remember? This is the covariance formula, right? Xi minus x bar, yi minus y bar, or x1i minus x1 bar, x2i minus x2 bar divided by n minus 1. N is going to be common, right? N or m here, the number of records, right? N is the number of records, right? So m minus 1 we should be saying. This is the formula for covariance. So we need to generate, first we need to generate covariance matrix, because the PCA is trying to extract the variance between features. We need to create a covariance matrix. On top of it, if we apply eigenvalue decomposition, that's it, right? We'll find the principal components, right? Do you agree? Do you agree with my statement?
Can you repeat, sir?
The principal component analysis main goal is to extract the variance between features. Okay. So to extract something out of some, right, some matrix, we have a tool, right? Eigenvector decomposition, right? Eigenvector, eigenvalue decomposition. That far good, right?
Yes, sir.
Eigenvector decomposition, what it does, it is actually extracting essence from a matrix. Okay. Principal component analysis is actually trying to look, right? It's actually trying to extract essence from variance matrix, or between, you know, features variance. So if you create a matrix that actually represents the feature variance and apply eigenvector decomposition, principal component analysis is done, right?
Yes, sir.
The tool we have is eigenvector decomposition. The tool is actually be able to extract essence from a matrix. The principal component analysis is looking to extract variance between features. Okay. So if you somehow produce a variance matrix, covariance matrix, then apply our tool, right? Use our tool, then PCA is done. Okay, so let us see that. Now decompose feature matrix using eigenvectors and eigenvalue decomposition. Eigenvectors, the covariance matrix, the covariance matrix are the principal components. These green and yellow, right, orange and green lines. Right? Eigenvalues are the number quantifying the variance explained by each principal component. Okay, this concept is not that easy, right? I am actually trying to explain and you are getting it well. Even if it is slow, don't be worried, you are getting it well. Okay, so take principal components with highest eigenvalues and multiply them with original data to generate PCA transform data. This last part, right? Take the principal components, this green and orange lines, and then multiply that with your original data. That is actually shift and rotate. Till here we found the direction. Right? After multiplying your original data with eigenvectors, we found the shifted rotated z values. Okay, let me show you with an example. Then we'll stop for questions. So here I have taken the original data. There are 5 columns. Right? Just now a question, right? Whether there are 5 columns or 5 million columns, it is going to calculate the centered matrix. X1 minus X1 bar, X2 minus X2 bar, X3 minus X3 bar, right? Like that. So X bar is mean. I am calculated mean of the first column, subtracted it from the same. Mean of the second column, subtracted from the same. Right? This is mean centering. Right? This data we took, and then we did mean centering here. Okay, that part is done. There is a purpose for mean centering. Okay, now I took the XC, that is centered data, right? I called it as XC. X is the original data. XC is the mean centered data. Right? I am transposing that matrix. Right? If I transpose this matrix, right, columns become rows. Do you agree? This far we are clear? We are clear, right?
Yes.
sir.
Now I am multiplying X transpose with X, XC transpose with X. See this here, the first column, first cell, X1 minus X1 bar, X1 minus X1 bar, right? X2. So it is between X1 and X1. Okay. It's a covariance between X1 and X1. Do you agree?
Yes, sir.
If I take only two columns, right, you will get it more clearly. Give me 1 second. Let me show you with the two columns only. X1 and X2 only if I take, right, it will be more clear. I took a bigger one because, you know, it shows a little magnified version. So we are now PCA is looking to extract the covariance between the columns. We are creating a covariance matrix. Right? We are creating a covariance matrix now. So let me take a screenshot. Right? If you have only X1 and X2, only two columns, X1 and X2, only two columns are there, right? M number of values are there, right? Then it's going to be M minus. So now, if you mean center this, what happens? It's going to be X1 minus X1 bar, X2 minus X2 bar, right? Now, if you create a, this is XC, right? XC transpose X is going to do what? The XC transpose also I will put is equal to X1 minus X1 bar, X2 minus X2 bar, right? So there will be no M number of rows there, right? So now you multiply this matrix with this matrix. What happens? This row multiplies this column, right? That's going to be X1 minus X1 bar into X1 minus X1 bar, okay? And then this row, right, XC transpose X, so I am going this direction, right? This row multiplies this column, right? X1 minus X1 bar, sorry, X1 minus X2 bar. So this row multiplies this column. So this row multiplies this column, it's going to be a, I am getting confused. Oh my God.
It's X2 minus
X2
bar.
minus X1 bar, that is. And this is, this one is going to be, right, this row multiplies this column is going to be X2 minus X2 bar. This row multiplies this column, right? So
Yeah.
into, sorry, I should put X1 minus X1 bar. Let me take another color to denote arrow. Okay. So this row multiplied this column and we got this. This row multiplied this column, we'll get this, right? So X1 minus X1 bar into X2 minus X2 bar, right? And here it's going to be the second row multiplying first column. That's going to be X2 minus X1 bar into X1 minus X1 bar, X2 bar. Sorry. And here it is going to be, right, this row multiplying this column is going to be X2 minus X2 bar into X2 minus X2 bar. So these diagonal values are going to be covariance between the same columns. Why am I saying covariance? If you divide whole, you know, this XC transpose X matrix with M minus 1, whole matrix you are doing it, whether you do it or not, it doesn't matter. Do you agree? Whether you do this division or not, it doesn't matter, right? So this is actually covariance. This is covariance between X1 and X2. Right? It's a symmetric matrix. Right? Upper triangle, lower triangle equal. You know, the diagonal is going to be the covariance between the columns itself. Right? This is a covariance matrix. Now, if I apply eigenvalue decomposition on this, right, I'll get the covariance essence from the data. Do you agree? Do you agree? Any confusion? Okay, good. So I have taken this bigger matrix because there is going to be sigma k is equal to 1 to m, right? K is equal to 1 to m number of rows, right? Divided by m minus 1 it is. It's not m minus 1, I think. It's m by m minus 1 only. Okay, that's fine. We'll correct it later, right? So here you see this, I have taken only one, two columns there while writing. So it looked like simple thing, but if you do it in a bigger way, right, it's going to create a square matrix. Original data may be rectangular, right? But after doing now covariance, like the centering and multiplying the matrix with itself, right? What we did here, we centered and multiplied the matrix with itself. We got a covariance matrix. Now we take this xc transpose x and then do the eigenvalue decomposition. xc transpose x is the square matrix that eligible to decompose using eigenvalue eigenvector decomposition, because you cannot do eigenvector decomposition on a rectangular matrix. And PCA is actually looking to extract covariance from the data. So in both ways, right, whatever we did is reasonable. We actually calculated a covariance matrix. Now the matrix is eligible. We did covariance extraction. So if you have million columns and 10 rows, right, you will get a million by million matrix. Got it? Here I have 5 columns, right? When I calculated covariance matrix, it is between columns and columns, right? So I have got 5 by 5 matrix. If you have 10,000 column data, it doesn't matter how many rows are there. 10,000 rows and 1 million 10,000 columns and 1 million rows. Even then you will get 10,000 by 10,000 matrix. Okay, you will get principal components as 5 by 5, and you will get the explained variance ratio, we call it as. This is eigenvalues. This value belongs to first principal component. This value belongs to second principal component. This value belongs to third principal component. This value belongs to fourth one. This belongs to fifth one. When I say belongs to, right, this number quantifies how much essence the first principal component extracted. This number quantifies how much the second principal component extracted. Right? This number explains how much the third principal component. This number explains how much the fourth principal component, like that. So each principal component is a direction like this, and then the eigenvalue actually tells you how much essence. And when you apply PCA, right, PCA always keeps these in descending order. This is going to be big number, a little small, a little small, a little small, little small, like that. When I say little small, right, the associated principal component is going to be the first one. The associated second principal component is going to be the second one, like that. The eigenvalues are going to be in descending order in the diagonal matrix. Similarly, the same corresponding principal components are going to be kept in order in the the PC matrix also. Got it? Got it? Any questions? Any questions? Okay. Now the actual transformation is happening. See, I have 5 columns here in my original data, right? So till here, if you see this, right, I took the original data, then centered it, and then multiplied the matrix, centered matrix with itself to generate a covariance matrix. Once after I have the covariance matrix, I actually did eigenvalue decomposition to find out the extract or the essence, the direction in which the most essence is present. The first one is going to have more, second one a little less, third one a little more less, like that. And then I took only 3 principal components from here, first 3, because they are the most essence extracted principal components. I have taken only first 3. You can take 4 or 2 or 1, it doesn't matter, right? It depends on how exactly you wanted to do. I took 3, right? I took 3 and multiplied my matrix. My original matrix is m by 5, m rows and 5 columns. I have taken 5 by 3, right? Only 3 principal components. Now I am multiplying my m by 5 matrix with 5 by 3 matrix. I'll get m by 3 matrix, right? M rows and 3 columns. This is the ultimate transformed matrix. When you apply PCA, this is what happens. It takes your original data, mean centers it, multiplies the mean centered matrix with itself to generate a covariance matrix. Now we apply PCA. PCA will extract essence from the matrix. What is the essence here? The covariance. It extracted, right, essence, and it kept in an order, right? And then I have taken the best 3 principal components and multiplied with my original matrix. Shift and rotate operation I did here. Then I have got the transformed data. This is the most essence, right? Most covariance, ultimate most covariance extracted from my original data is going to be this Z1, Z2, Z3. So this is the ultimate sugarcane juice, right? So this you cannot figure out, from how much you got from X1, how much you got from X2, how much you got from X3. It is all crushed and kept out, right? What you pulled out, whatever essence from the data. This is the PCA. Got it? Now we'll see code. Right? While looking into code, right, we'll know more. But all questions are answered. Most of the questions, maybe.
Sir, what are the values in this PC1, PC2, and PC3? Let's take from the graph. So where we have drawn PC1 and PC2.
This one, right? The green line, the vector is going to be the green line and orange line vector. If you have only 2 variables, right, you will have only PC1, PC2, right? The vector is the
So the PC1 here we have 5 values. So that means
5-dimensional.
The x is the x coordinate of all the points from the green line?
No. Here we have only 2 coordinates, right?
Yes,
Here we have only 2 coordinates, right? Only x1 and x2, right?
Yes.
For green line, you will get 2 values. When I say 2 values, right, it's a vector you are saying. When you say vector, right, from origin, it will actually go in that direction, right? If you see this, right? So this is the origin, and there will be 2 values, maybe coordinates, maybe here or maybe here or somewhere, right? That's the direction, right? That line you draw like that. And for this also, you will get 2 coordinates. But the example I have taken 5 coordinates there. That means it's a 5-dimensional matrix, 5-dimensional graph. It's going to be plane or hyperplane, we call it as, right? There will be flips and all that. If you have 3 coordinates, it's going to be plane. Got it?
Yeah, that's correct. But so on the graph, so whatever these dots on the green line, whatever these dots represents input data, transformed input data kind of stuff after projection.
This is the transformed projection, everything. This is the
multi-steps.
Yeah,
right?
your question is
that was the
this
first
Z1, Z2, Z3 or this one. The projection and rotation happens in a single shot. When you multiply your PCA, the principal components with your data, original data, that's when this happens.
This is actually Z1, Z2, Z.
These dots are the Z1, Z2, Z3 values.
So what is that? The PC1 and PC2, PC3. So is it taken
These lines,
from the above
green
step?
line and orange line.
Before rotating?
No, there are 2 things actually. There is a direction and there is rotation, right? There is There is transformation and direction. First we are finding direction. What is direction? The green line and the red line. They are not lines actually. They are the coordinate. They are the data points. When you represent a data point as a vector, you draw a line. Right? Do you remember that?
Come again, please.
See this here? This is a data point, right?
Yes.
V1, V2 is a data point, right? I actually drew a line from origin and said that, there is a direction and magnitude. Why did I say? Because I am saying that this is a vector. When I say a vector, a data point, a vector, you will actually draw a line like that it is. So here there is x1, x2. For there is some dot here, x1, x2, and I am saying it's a vector, so I am actually drawing a line through origin. That is principal component 1. Still confused?
Yes, sir, but we will move forward and we will discuss further later.
Okay.
So this V1, V2, we have only 2 because it's in 2-dimensional. If it is more than that, then we will get more. So
Plane, it will become.
Yeah,
if it is 3, right? It will become plane. If 4, hyperplane, right?
Yes.
No, you will have 2 planes, intersecting with each other. 3 planes, 4 planes, right? N-dimensional space you cannot imagine, right? I cannot basically.
So the
2-dimensional. Yeah, please.
Yeah. So the PC1 column at the point of multiplication, there we have in PC1 we have 5 values, right? So those are.
If you look at this diagram and trying to talk, PC1 will have only 2 values. PC2 will have only 2 values.
In multi-dimension.
Because
in
only
5 input variables we have taken, right?
Then no 5. Yeah.
It actually all the 5 in the column represent only a single point in the hyperplane.
Hyperplane, you may say, if there are 3 points, right? It's a globe. It's a kind of ball, right? More than 3, it's going to be, 2 balls interacting with each other. Maybe it's like many balls actually coming close to each other, kind of a thing. It's a dot, basically. Yeah, it's a dot.
It's a dot. So the every
But
dot.
when you say a vector, you represent like this. You represent like this. The same thing, I actually extended it to backward and forward. That's it. Here.
Yes, sir. Please go ahead.
Okay. Anybody has got any other questions here? Okay. So let us look at the code a little more and then try to understand. Maybe this will clarify more. Right. So now, right, I have to point one thing here. So if you have multi-collinearity in your data, right, if you find PCAs and transform, right, the principal component analysis, you apply principal component analysis and then transform your data, your multi-collinearity will be gone. Z1, Z2, Z3 are going to be independent of each other and they will extract all the multi-collinearity from the data. Do you agree? Do you agree? I made a statement. If you apply PCA, the multi-collinearity in the data is going to be extracted, is going to be eliminated after you find these Z1, Z2, Z3 values, right? The multi-collinearity in the data is going to be gone. No multi-collinearity. Do you agree with the statement? Do you agree with the statement?
Yes, but in real-time code, maybe do we have any parameter, hyperparameter kind of stuff which applies on
and
the
try to see
eigenvalue?
how many to extract or eigenvalue.
Yeah.
Eigenvalue. I'll show that. that whole practical implementation I'll show you in a moment. But do you agree with my statement? If yes, why? Should I repeat the statement? Once after applying PCA and transforming your data, right, x1, x2, x3, and so on, x5 has become z1, z2, z3, and so on, z5. No? If I take all 5 principal components and multiply with my data, I'll get 5 z1, z2, z3, z4, z5. Okay? The z1s, right, z1 columns will not have multi-collinearity. That's the statement I made. Will not have multi-collinearity. Is that a right statement?
Yeah,
Z1,
my
Z2,
understanding
Z3
is
will not.
my understanding is because we found eigenvalue lambdas, and some of them became only lambdas are there in the diagonal only. So that is where the multipolarity is removed. That's my understanding.
No, sir. And, lambdas are just quantifying, right? Which one is the best extractor out of all the principal components? It is just letting you know which principal component is the best one. When I say best one, right, which one is the green one, which one is the orange one, which one is like next one. Green one I am saying because it is extracting the most essence, in the direction in which the covariance is present, right? So anybody else would like to agree, disagree, make a statement on this? Multi-collinearity will be gone in this data.
So they are actually, okay, go on, please.
Yeah, I'm thinking like maybe we have reduced the number of vectors, right, columns. So the collinearity between those vectors got reduced. I mean, it's lost.
Yeah, maybe, right? See here what we are doing here. We got the correlation, right? Covariance is nothing but correlation, right? Correlation is the standardized covariance, right? So multi-collinearity means there is correlation between features, right? More than 2 features have got correlation. You call that as multi-collinearity. We created a covariance matrix and then we found the principal components. That means the extract of each column, right? And then we transformed our data. That means the extract actually, kind of figured out all the there are 4 columns which are very strongly correlated. It would have got everything into Z1. The other 4 columns, maybe, other 10 columns may have other correlation. It may have got into Z2 like that. So it is an extract of the correlation, right? Each one is going to be independent. After you transform the data, Z1, Z2, Z3, and so on, Zn are going to be independent of each other. Right? All the dependencies between input variables is been extracted and you found the ultimate thing. So multi-collinearity, if you have in your data set, the solution is PCA. You need to apply principal component analysis, then you get multi-collinearity eliminated. Okay, or you do regularization. Some of the coefficients or features will become small and big. That way, it gets balanced. The multi-collinearity will get balanced. Okay, the solution for multi-collinearity is either you do regularization or apply PCA. Okay, now let us jump into the code. Don't wait, and you will get more clarity. And tomorrow we'll see a little more, kind of understanding and discussion we'll do. So this is the most important thing. You should not reduce the data and then try to do the supervised learning. And this point, right? I do not agree with this point. So some people, what they do is, if you have 100 column data set, right? They reduce the dimensionality to 2 columns using principal component analysis and then do a 2-dimensional plot. I'll show. I'll show what I meant here. But when you actually take 100 column data and reduce it to 2 columns, you will lose essence. Okay, that diagram is not going to be useful. Some people are very fancy about looking everything in a pictorial way, but we cannot. You should always have a thought process where by looking at numbers you should be able to understand. Okay, so I'll talk about this later. I've taken the whatever is needed, and I've taken the same digit recognized data set. So in the digit recognized data set, there may be some correlation between the pixels. Yeah, basically, right? When you look at any picture, in the middle only you are having those numbers, and rest all is going to be zeros, right? So there is some multicollinearity in this data. So I am trying to apply PCA and trying to extract it or reduce the columns, right? There are 784 columns. I am trying to reduce the columns to maybe 400 or 200 and build a model and see how it's working. Okay, so in a way, to make the supervised learning algorithm run fast, I'm using PCA to reduce the number of columns. Okay, so I've taken the data, I did something. There are hyperparameters like n components, right? N components can be a real number or a integer. If you specify n components as an integer, that will extract, in this example, right? I extracted 3, right? So if I say n components is equal to 3, that's going to the PCA algorithm will actually take the first 3 principal components and then multiply my data and find out this. If I say 5, right, it's going to get 5. If I say 2, only 2 it will take and multiply and produce this. So that is n components. Okay, you can specify integer. If you specify integer, that many columns will be produced. Z1, Z2, Z3 will be produced if you say n components is equal to 3. No, if you want to give a real number, that number should be between 0 and 1. If you say 1, right, it is going to get all 5 columns. If you say 0.5, right, it's going to get 2 columns only, right? 2.5, or maybe there are 5 columns. I don't know how it works. Maybe 3 or 2. It will actually bring, so it is ratio, right? Out of 100, 1 is 100, 0 is 0, right? Out of 100, how many you want to get? 0.5 means 50% of the principal components you want to take and apply them, shift and rotate. Okay, so explained variance ratio is nothing but the eigenvalues. Okay, eigenvalues of the data. Let us look at a simple example and then we'll talk about these theoretical things. So PCA is the algorithm, and I said fit transform. I actually took a digit recognizer X train only. See this? No, there is no Y. Okay, when you look at this whole thing, I took only X, no Y. I took X, centered, found the the covariance matrix, then found out the eigenvectors, then multiplied those vectors with my data and found out the whatever, right? So I took X only, right? Fit transform I did, and now if you look at fit transform PCA, see, it actually got the same number of rows and same number of columns. Why? Because I did not specify n components here. Okay, did you get this point? If I specify n components is equal to 10, right, it would have got only 10 columns there, right? 33,600 rows and 10 columns. Okay, I did not specify anything, so it took the whole data and then all the principal components and multiplied. The PCA, the components underscore, right, is one attribute, and explained variance ratio underscore is another attribute. The components underscore will give you eigenvectors, but it will give you a transposed eigenvector. So I am actually transposing it and showing it. It is theoretical, right? The implementation was like that. So the PCA will give you transposed eigenvectors. Okay, I am transposing it again and trying to look at the shape. Okay, don't look at this transpose. No, don't forget about that part, right? So there are 784 columns, and you will get a 784 by 784 matrix. That is the eigenvectors. See here, there are 5 columns. Right? There are 5 columns. You calculated 5 by 5 covariance matrix, and then applied eigenvalue decomposition. Right? You got 5 by 5 eigenvectors. Got it?
If they are independent, they'll be 5 by 5. And even if it's not independent, but the eigenvalues are going to become 0. Okay, so these can be got from the algorithm using components underscore. Okay, I showed you math to do eigenvalue decomposition and all that. There is no need for us to do it. Pca algorithm will do it, and it will give you also. Okay, and explained variance ratio underscore is the eigenvalues. See these eigenvalues? Explained variance ratio underscore. Only 10 I am looking at. There are 784 values. For each eigenvector, there is going to be an eigenvalue. Right? And then I said these eigenvalues are going to be in descending order. Right? See this? 0.09, 0.07, 0.06, 0.05. Right? The first eigenvector extracted 9% of the essence or 9% of the covariance or the multicollinearity, right? And second eigenvector extracted 7% of the multicollinearity from the data. Third, 6%. So how much percentage you want? How much percentage of the covariance from the data or multicollinearity from the data? Basically, the principal component analysis is extracting the covariance from the data. If your data set has got very strongly correlated data, very strongly correlated columns, and they are the most effective ones in predicting the target variable, you apply PCA, take the applied PCA applied data and build a model. It will work as equal as your original model, original data and original model. Did you get the statement? Basically, these eigenvalues are showing you how much each of the principal components, 784 principal component, 784 eigenvalues. Each principal component will have its own eigenvalue, which explains the amount of multicollinearity actually extracted from the data. Right? That point is clear. That point is clear.
So the explained variance ratio is the eigenvalues. So eigenvalue, if the eigenvalue is more, so then we say the relation between those two variables is high.
No. You see, after applying the PCA, you don't know which feature is what.
So it's actually the lambda 1, lambda 2, lambda 3, right?
Lambda 1, lambda 2, lambda 3, and if you look at this diagram, right, the first column and the first column and the lambda 1, the second column and the lambda 2, like that it is, right? So this one is saying that the first principal component extracted 9%, 9.7% of the covariance in the data, multicollinearity in the data, not covariance. Multicollinearity, if I say what, from all the columns in the data, 784 columns, there will be some correlation, right? So when you take any data set, there will be some multicollinearity. You cannot take a data set with all independent columns, you will not get, right? There may be some columns which are completely independent, but there will be columns which are completely dependent. Let me tell you one point. If you look at this data, right, there are zeros, right? The columns with zeros are all multicollinear, right? Columns with zeros are all multicollinear. One is decreasing, another is decreasing or increasing. Zero it is basically, right? And there will be numbers also like that. So that is what is. It doesn't know whether it is from between first column, second column, first column, third column, first column, 784 column. It is from all columns. This is also from all columns. This is also from all columns. But each one will try to extract some, because if you look at this diagram, right? See this? This one extracted some. This one extracted some. Like that, 784 lines will be there. 784 vectors are going to be there. Principal components are going to be there. Each one will extract some. Got it? No? Yes.
The graph is not visible, sir.
Huh?
Have you drawn the 784?
No, 784 I cannot draw. How can I draw 784?
Just show
784
you.
dimensional matrix. No, this one I am showing you. This is 2-dimensional as an example I am showing you. Can you see my screen?
No, I think screen is stuck.
Code.
Screen is frozen.
Oh, okay. Let me stop sharing and start it again. It's down thing, right? So maybe now it's visible, right?
Yeah, yeah.
Is it visible now?
No,
So
you are.
see, this one extracted some, this one extracted some.
No,
Like that,
sir.
each principal component will extract. Yeah.
You're seeing blank screen, black screen.
Your name only, yeah. On the Teams, your name only.
Oh my goodness.
Now we are able to see.
Now we are able to see.
Oh, okay. It's a dangle thing, right? Maybe that's problem. Now you can see, right? Right?
Yeah.
This
Yeah.
one and that one. Right? And, if you have 784, right? Then there will be 784 planes. They are. I cannot imagine how it's going to be. So that's like that, right? Got it? Got it? Can I move on?
Yes, please.
I look at, I'm actually showing only 20 explained variance ratios or eigenvalues, right? Let us see, right? How much extract you want to, how much essence you want to extract. I just took 300 of these eigenvalues and summed them to see what I'm getting here. 0.986, that means 98.6% of the essence can be extracted if you take 300 columns. When I say if you take 300 columns,
yes, sir. That is
you can see my screen, right? So you imagine that there are 784 columns here, and you have taken 300 principal components and multiplied them. Then you get 33,600 by 300, right, as the outcome, right? So that's going to have 98% of the multicollinearity from our data. Do you get the statement? If I take first 300 principal components, right? First 300 principal components, n components is equal to 300. If I say, what happens? It takes first 300 components and multiplies my original data, which is going to extract 98% of 98.63% of the explained variance ratio. Z1, Z2, Z3, and so on. Z300 will have 98.63% explained variance ratio or multicollinearity. Got it? Got it? Yes, no?
So we are going to, if this is the case, we are going to consider these first 300 Z1, Z2, Z300 and then build a model.
Yeah. Well, I'll show that in a moment.
But we are talking about these, 300 has more multicollinearity. We should not consider, right? If the multicollinearity is more, we should eliminate.
No. Multicollinearity. Yeah, that's a good point actually. Should we be eliminating or should we be considering, right? Multicollinearity is not a problem. Multicollinearity will make your if there is relationship between input variables, it is not going to be a problem. If there is relationship between input variables, unnecessarily you are considering multiple variables. Now, suppose that there are 10 variables, they are strongly correlated. All have got one correlation or -1 correlation. If you take one column, that is enough, right? Do you agree with the statement? Should I repeat?
Yes, to some extent. It may lose a bit
No,
of
no,
essence.
not to some extent. No, it is yes. If you have 10
No,
columns in your input data, no, no,
if they are
If you have
100%
10 columns,
related, yes.
yes, right?
If they are
So they are
100%
90%
related, yes.
related.
Yeah.
If they are 90% related, then also some part of it is unnecessary, right? Some part of the second column is unnecessary. If the two columns are 90% related, right? Some part of first column is unnecessary, some part of second column is unnecessary, right? So in that way, if you apply PCA, right, that unnecessary thing will go off and it will actually extract only that essence. Or sometimes it may cause problem also. If that unnecessary thing, right, the 90% relation is there, in the first column and second column, there is some important thing which is not being captured by explained variance ratio, but that is useful in predicting the target value. That will be gone. That's the loss. When you apply PCA and try to use the applied PCA data to build a model, that is the loss. I think you are on the right path, right? Right path, and you are thinking right. I don't know whether I confused you or corrected. I actually explained it properly. Got it? So the point I wanted to make is, when you apply PCA, you cannot say it is always right. If it works, it is right. If it is not working, it is not right. But basic understanding you should have is, if most of the multi-collinear features are the predictive, are the features which have got more predictive power, then applied PCA, data will be more useful in building a model that runs quicker. That runs quicker because number of columns reduced and the essence is already there in the data. The essence is what is useful in predicting the target value. If that is not the case, the multi-collinear columns are not the columns which have got most predictive power, then applying PCA will not give any good result and it will actually deteriorate your model's accuracy. Got it? Got it? Yes, no?
Yes.
Shishiramu? Huh? Yeah, Girigari. No?
So
What you are thinking? Let me know what you are thinking, then maybe I'll be able to answer.
I was just thinking what these values exactly represent. Is this, we have taken 20 values, right? So they are in the order.
I am just showing you 20 values only here.
Yeah,
You can look at all.
Yeah. But the first value is representing the multicollinearity between all the variables, or it is the essence taken from each value and made this value. Each input variable and
All
made
the
this
variables. All the variables. How much
It
the
is the
first principal
essence or the
component is getting?
multicollinearity.
Quantification. Essence is present in component, principal component. Quantification is present in the explained variance ratio. Essence is present in the eigenvector.
Yeah.
Quantification is present in the eigenvalue.
But it's not the multicollinearity, right?
Quantity, right? How much multicollinearity this is, and multicollinearity is present in this the component.
Okay, that's the only confusing point, because if the multicollinearity is more, so we should ignore them. So let's say we are taking 20.
No. We should not ignore. We should not ignore. According to principal component analysis, it is considering the multicollinearity.
Okay, so if that is the case, let's say in this case 784, we are actually trying to take maybe 200 first reports or whatever.
First principal component.
So first principal components. So we are actually taking those values which are actually having more multicollinearity, and we are ignoring those which have less multicollinearity. So if we have the less multicollinearity, so those are actually independent values or independent data.
Yes, independent variables. Yes.
That's where I confuse. Like we should always try taking the independent data so
It
that we
doesn't
have the
matter.
different
No,
variants, right?
I think you are thinking right, but the small confusion is which should be considered, which should not be considered. You already predefined. No, don't define it. It is the algorithms approach. We are trying to understand algorithms way of doing it. Got it? You have some understanding that is right. Whatever understanding you have is right. When you are building a supervised learning model, right? What your understanding is whether there is, in reality, what should it do is if there is multi-collinearity, it should ignore. If the features are independent, it should consider. That's the point, right? You are trying to make.
Yes, that's correct.
That's the point, right? So that is correct. Even I say that is correct. Okay. But here, when you apply PCA, the PCA works like this, right? Wherever it is useful, use that. It's a tool, right? You have a hammer, you have a chisel, you have, an axe, right? Whichever is useful where you need to decide and use it. The PCA is what it is doing is it is extracting multi-collinearity and creating consolidated columns. Okay, creating consolidated columns. So that's the point I made. There is a data set, right? There is a data set which has got huge multi-collinearity in the data. And the multi-collinear columns are the most important features in predicting the target variable. On that dataset, if you apply PCA, the model will work best after reducing dimensionality also. Okay, that is one point. Where to apply PCA? I made a statement. When there is multi-collinearity in the data, and the multi-collinear columns are the ones which are, majority columns in predicting the target variable, then you should be applying PCA. Where you should not apply PCA, that's the point you are talking. Where the PCA should not be applied is the point you are talking about. When there are independent columns and those are the columns which have got most predictive power, you should never apply PCA on that data set. Got it? Your point is right, my point is also right. There are two ways, two different kinds of data sets where you should be applying PCA, where you should not be applying PCA. Got it?
Yes, sir. With this application points, yes, it is making sense now.
Yes. You are correct. Actually, you are thinking right. But there are different tools. The tools work in different way. Where we should be using the tool, we should decide. We are actually learning the tools. That's it. Got it?
Yes, sir. Yes, sir.
Good. I think you guys are getting it right. After a long time, right? I see that you guys are getting it right. See, to understand PCA, I took around 2-3 months. Believe me, to come up with these diagrams, this whole thing, right? I took around 2-3 months. I am trying to explain that in 3 days. That's not a simple thing to understand in 3 days. Engulf everything in 3 days. I am trying my level best, and you guys are doing it well. And by tomorrow, right, you will have complete clarity. Believe me, you will have complete clarity. Okay. So I took 300 columns and tried to show some, because if you take first 300 columns, and then multiply your like this. If you do this operation, right, take the original data, first 300 columns, multiply it, you get 300 columns which will have 98% of your multi-collinearity. Will that be useful or not? That's the secondary thing. We are doing unsupervised, right? Unsupervised operation now, right? We are taking only X. We are not considering Y. And is it be useful or not? We are not bothered about it now. We're just trying to apply that and see what's happening there. Okay. So do I need to do this operation? No. If you just say PCA and fit transform, it does it. PCA, right? If you say fit transform, when you say fit right, it will do all this. Right? When you say fit, it will take the original data, it will do centering, it will actually find out the covariance matrix, it will find out the principal components and the explained variance ratios, right? The eigenvectors and eigenvalues, And then the transformation is what is this operation is all about. It takes the n components 3. If I say it takes first 3 principal components, multiplies by matrix and generates this. This is transform operation. Till here it is all fit. Got it? For every algorithm, for every class, or for every transformer and the predictor. Transformers are these standard scalars, polynomial features. These are all transformers. Right? Predictors are the algorithms. Every transformer and predictor will have its own fit and transform operation. Right? Here the fit operation is big. You take the data, do centering, you find out the covariance matrix, you find out the principal components. That is fit operation. Transformation is take the n components and multiply that with your data and produce the result. Right? That is transformation. So you no need to do anything there. Whatever we have seen theoretically, I just tried to dissect everything and show. Okay? Because when you look at PCA, this is the most complex thing to understand in machine learning. But understanding this thing actually helps you a lot in many other places, like recommender systems and other places. Okay. So I have taken n components is equal to 20. Here I did not took any PCA. I did not specify n components there. I have got same number of columns after applying. These are Z1, Z2, and so on Z784. Okay. So here I am taking 20 components and doing fit transform. I am getting 20 columns only. Okay, this is our operation. 3 components and then multiplied 3 columns I got. Like that, 20 components, fit transform, I am getting 20 columns. So if I say 0.95, right, 95% of the explained variance ratio will be extracted. Right? 95% of the explained variance ratio, how will you know? Here if I take 300 columns, right, I've got 98%. Right? If I say 95%, right, 154 columns. If you take 154 eigenvalues or the explained variance ratio and sum them up, you get 95. So that's where it actually got to know it is 95, 154. See, I did this. So all the explained variance ratios I tried to show here. So it started with the 0.097. Right? Somewhere it will become 0. E to the power of E is 10 here, E to the power of 6, E to the power of 7, E to the power of 34. Right? Beyond this point, right, I think these are all zeros, close to 0. Right? All the last principal components are close to 0. Okay. So here I cumulatively summed it. Right? See this here. At one point in time, it'll stay at 1. See this here. These are all right. Beyond this point, at whatever the explained variance ratios are all close to 0. Our Python is unable to calculate more. So that's where it made it, rounded it off to 1. Right? So if you take this many columns, right, that's enough to extract the explained variance ratio. Total 100% explained variance ratio can be got by getting. So if you take argmax, right, argmax of this cumulative matrix, right, in 696. 690 n components is equal to, if you say 696, then it will get the 100% explained variance ratio from the data. Okay, so I'll show you more approaches tomorrow on deciding how many components to pick. I think today it's too much. Let us talk about that tomorrow. Any questions, right? I'll answer.
Sir, probably for the explained variance ratios,